Let's talk about logistic regression. Before we talk about logistic regression, let's just quickly recap what we did yesterday. So yesterday we talked about linear regression, and in linear regression we were modeling a continuous response variable or continuous label, and we were modeling it as a linear function, which in the one-dimensional case is just an intercept and a slope times our one-dimensional input, and we were modeling it as this function plus some noise term here. So now we want to see what happens if we move from this continuous response variable to a discrete response variable, which could be a label in a classification problem. This label could be spam, not spam, for example, and we generally label it as 1 and 0, which could be true and false, could be spam and not spam, cancer and no cancer, and so on. And so let's just look at a very simple example. So this example I mentioned is the Wikipedia example, because if you look at for logistic regression in Wikipedia, you will see this example here, and it deals with the case of students, a set of observations from 20 students which have studied for an exam, and you will see in the plot how many hours they have studied and whether they passed or did not pass the exam. So down below are the students which did not pass the exam. So here's the response variable is pass, and it only has two labels, 0 and 1. 0 is not passing and 1 is passing. And down here the hours studied. So this guy here did study 2 hours, for example, and he didn't pass. The guy up here just studied a little bit more than 2 hours, but he did pass there, and so on and so forth. So this is a person which studied the most, passed as well. But some people did study quite a lot. They just studied 3.5 hours, but still did not pass. So this is the data, and I just plotted it, labeling passing and not passing as 1 and 0. I just plotted it in this space, and obviously the question is, how am I going to model this discrete observations here? And the only continuous thing I could model, because if I want to model it using the techniques from last week, I have to model something continuous, and the only continuous variable related to it would be, say, the probability. So I could look at the probability of passing and not passing, and actually if I would fit a linear line, if I would just close my eyes, don't know anything about logistic regression, say, okay, I have this data points here, let me just plot a linear line through this data point, just do a linear regression on it. I will get this red line here, and this red line actually doesn't look too bad. It could be, if I interpret it as a probability of passing and not passing, it would be a reasonable fit to the data, where I just say, okay, this is the probability, here's a half. If I say everything which has probability above a half is classified as passing, and everything at probability below a half is classified as not passing, then this would be a reasonable model. The only problem here is that obviously it's not a probability, as you have probably just guessed right now. This function here can be below 1, and it can be above 1, it can be below 0 here as well. So that's obviously not a good function for probability. But if I had something which would be looking quite similar, but at least it would be always bigger than 0, so here it would kind of be flattening off, and then it would be always staying below 1, so here it would be flattening down, this function here would be a reasonably good model for the probability. And you see, it's not too far from the linear model, and actually such a function which looks like this exists, and it's called the sigmoid function, and this is exactly the one we will be using to model it. So the function which has this form is this function here at the bottom, which is sometimes called the sigmoid function. So let's just write it out one more as e to the x divided by 1 plus e to the x. And this is sometimes, let's just call it s, the sigmoid function, s of x. Now, you can also write it in a different way. If I just divide through by e to the x above and below, I will just get 1 divided by 1 plus e to the minus x. So this is just a different way of writing it. So you might see it the one way or the other way. Importantly, let's just look at some points and see whether it has the right behavior as shown in the plots there. So for x equal to 0, so s of 0 is just, if you look at the last expression, it's just 1 divided by 1 plus e to the 0, which is 1. So it's 1 over 2, it's a half here. So at 0, this function is exactly to a half, which is good. And when it goes to infinity, it will go to 1, or it should go to 1, as I see from the plot. So let's just quickly check this. So the limit of x going to infinity of f of x. So the easiest way of seeing it is if I look at this expression below here, it's 1 divided by 1 plus e to the minus infinity, which is 0. So it's 1 divided by 1, so it's 1 here. And similarly, the limit when x goes to minus infinity of s of x is given by, should be given by 0. And that's maybe easier to see as the expression above here. If I have e to the minus infinity will go to 0 divided by 1 plus e to the minus infinity, which is 0, which is 0 divided by 1, so it's 0 here. So this function has exactly the kind of bright properties. It goes to, asymptotically approaches 0 to the left, asymptotically approaches 1 to the right, and in the middle is a half. So this function is called the sigmoid function. And what I do in logistic regression here is, rather than modeling the continuous output in linear regression, I now model the probability here, and I model the probability as a sigmoid function of a linear function f of x. So let me just kind of write it out to make it clear. In linear regression, let me choose a different color. In linear regression, I model y by a linear function f of x. This is just linear regression. Y is a continuous variable, is modeled as f of x. Now in logistic regression, I model the probability of the class label p. So p is just the probability that the class label is 1, and I model, this is a continuous function, but it ranges between 0 and 1, so it can't have any value, and this is why I model it as a sigmoid function of a linear function. So this is all there is for this is logistic regression. So for a standard linear model, I have the continuous output is a linear function, and here I have the probability of the class label being a sigmoid function of a linear function here. F is again a linear function. So this is all there is for the logistic regression. So hopefully it's a rather straightforward step, and this is exactly how it is defined. You might say, well, I could define it maybe differently, but this is the most common model. And you might ask me also, so why is it called logistic regression? Is because this term here, this p s of f of x, if I write out this function p is equal to s of f of x, which from the last slide is just 1 divided by 1 plus e to the minus f of x. So if I just solve this expression here for f of x, I will get f of x is equal to the logarithm of p divided by 1 minus p. You can just very quickly solve it. And this function here is sometimes called the logit function. And this is why it's called logistic regression, because I effectively, the function, the linear function, models the logit of the probability. And this is why it's called logistic regression. And so this is how it's defined, and hopefully it makes sense from the picture that this is a reasonable definition here. So effectively, all I want is to model this probability by this smooth function, and I do that by modeling the probability of the class label by a sigmoid function of the linear function f of x. So I hope that the motivation of this definition is now clear and intuitive, and hopefully the definition itself mathematically also makes sense. The question might be, well, how do we solve it? And so we do not have anymore this nice interpretation of least squares as we had for the linear regression, but we can still write down the maximum likelihood here. So the maximum likelihood estimation still works. So the likelihood, as we knew, is just a kind of product of the probabilities. If all these observations are independent, all I have to do is multiply the probabilities, or probability density function to be more precise. So effectively, given that P is the probability for the label being 1, so let's just call this P, I also know that the probability for this label being 0 is just 1 minus P. Basically, it's just, if there are only two labels, if the probability is P for it being 1, it must be 1 minus P for it being 0. So if I want to write down the likelihood, I only have to multiply all the factors. I have to multiply P if it's a label 1, and 1 minus P if it's a label 0. But this is exactly what this expression below does here, because if I put this exponent here, this exponent, if yi is equal to 1, then I will get the first term, and the second term will be something to the power 1 minus 1, which is 0, so this is just 1. So I get just a factor of P. But if yi is equal to 0, then the first term here, the first factor will be 1, and the second one will give me 1 minus P. So this will just be the product of P, 1 minus P, and so on, depending on whether the observation was a label 1 or a label 0. And this is exactly the likelihood here. And all I want to do is now maximize the likelihood, which we know is the same as maximizing the log likelihood or minimizing the negative log likelihood. So it should say negative log likelihood here. So this is how you can mathematically do it. So if you now have a computer, you can just, given the data, you just write down this function, and it depends on A0 and A1, because obviously P is a function of X, and X depends on A0 and A1. So it depends on those parameters. I can now just vary those parameters until I find the maximum, and then I have numerically solved the problem. So as long as you know how to maximize a function, the problem can be again solved as before. And effectively, if I look at the log likelihood function, I can again write the negative log likelihood function just as a, so this would be, this term here is the likelihood L, and last time we defined L as just the logarithm of L, and we can also, rather than maximizing L, we can also minimize little l, and this term is just a loss function. So similarly, as we had a loss function for linear regression, we now have a loss function for logistic regression, which is just the negative logarithm of this expression here in the brackets. And if you want to do a little exercise, you can just write it out yourself by taking the logarithm, then throwing the product inside of the exponential and writing it as a sum. You can just write this out to have a look how this expression looks like, and we will actually come back to this expression next week when we talk about support vector classifiers, because we will see that the support vector classifier actually has a quite similar loss function, which as this one here, but it's a rather more kinky loss function. But we can see some similarities with support classifiers there next week. But let's just move on there and have a look, how does it look like? So now we have defined the logistic regression, we have an understanding how it works, and we formulated the mathematical optimization problem, which you can use to numerically solve it. So just put it in a computer, take a solver, and it will solve it for you. Obviously, once you use the Python function logistic regression, everything is already built in, but this is what it does underneath the hood. If you ask yourself, well, what does it do if I call this function? It will just run this optimization here for you and find the maximum parameters a0 and a1. And here is where I have done that already. So actually the red line is exactly the line you will get if you run the logistic regression fitting function. And you can see that what I call the decision boundary is here. So here is about 2.8 hours is where I say everything to the left of this will have a probability which is below a half. So everything to the left is classified as fail, and everything to the right would be classified as pass. So obviously I classify those points here as pass, and those points are classified correctly. But the model would also class those points here as a pass, but there in reality they didn't pass. And similarly, the model will classify all those points here as fail, and also those 2 points would be classified as fails, and they would be wrong because they actually did pass here. So everything to the left would be classified as fail, everything to the right would be classified as pass. And those 4 points here, those ones and those ones, those are the ones which I got wrong, basically. And this is also one nice way of defining kind of how good the model is. I could ask, how many of these points did my model predict wrongly there? So for linear regression, a measure of error was root mean squared error, which we saw yesterday. And here for logistic regression, a possible measure of error would be the misclassification rate, which is a fraction of observations which I got wrong. So if I look here, I can define the misclassification rate just as what I just said, the fraction of points I got wrong. So mathematically, it would just be the sum over the indicator function when the predicted variable is different to the true label. The predicted label is different to the true label, so I will just sum over all points. If it's different, I will sum 1, and if not, I will sum 0. That's the same as counting. So this is just the number of observation where it's different. It's the number of wrong predictions over the total number of points here. That's what it means, basically. And I can look at the example. I already highlighted those were the points, those 4 points which I got wrong. So there were 20 in total if you count. So 4 out of 20 I got wrong, or 20% of the observations I got wrong. So the misclassification rate would be 0.2 or 20%, or otherwise I could say I got 80% right. So this is a good measure of error to use in the case of classification and logistic regression in particular. So far we've just talked about the 1D model. This is obviously, the plot looks 2D, but obviously the predictor variable is just ours. This is just a 1D variable, and this is just a probability here. But it becomes more interesting if I have more than one variable. So this is just univariate logistic regression, and I can look at multivariate logistic regression. Now, mathematically, the extension is rather straightforward. I write down the same relationship I had before. I model the probability as a sigmoid of the function f, where f now is a linear function of more than one predictor, in this case p predictors here. What's important to notice is that the decision boundary is it's when the probability is a half, because if the probability is below a half, I will classify it as class 0. If it's above a half, I will classify it as class 1. And this decision boundary is, we derived it before, is so when is this function a half is when s is equal to 0. This is what we derived before. So the decision boundary is just when f of f is equal to 0. And if I write down this expression here equal to 0, so 0 will be a0 plus a1 p1 plus and so on ap xp. This is just a linear function. So importantly, the decision boundary is still linear. So I have a linear function which if I had two predictor variables, it would just be a line, a linear function in 2D is a line. And this line will tell me everything on one hand to the line is classified as one label, and everything to the other side of the line is classified as the other label there. And I can look at one example here where I plotted a kind of extension to the previous example. Remember, before we had the hours studied, and now I also added the hours of sleep here, which I just made this up. But here you see, for example, if a person did study very little and kind of slept very little, like this person here, more likely to fail. And if you had slept a lot and studied a lot, like this one here, then you're more likely to pass. So the green dots are pass. This is label 1, and the red ones here, they are fail. So this is label 0 here. So obviously it looks a bit different to this plot here, because here I had just a 1D line and I plotted the probability in the other direction, but my input predictor is just a 1D line, and my decision boundary here is just 1 point basically in this 1D, in this line. Now if I go at one more dimension, then obviously my two predictors are already 2D, and the probability, if I choose to plot it, would be a third dimension. I haven't plotted it here, but you could think of the probability as being like a 3D function coming out of the plane. So it would be flat, close to 0 on the left hand side, then it would go up, would cross 1 exactly at the line, the red line, and then it will cross a half exactly at the red line, and then it will slowly approach to 1 further to the right. So there will be like a 3D probability function, which will be like S-shaped, but kind of like a sheet which looks S-shaped, basically, which is kind of flat and then moving like this. So this would be the probability, but then my predictor space is just 2-dimensional, and the decision boundary here would just be a 1D line. So I can write down the equation. So if you call, let's just say this is x1 and this is x2, then I know that my decision boundary is just 0 equal to a0 plus a1 x1 plus a2 x2. So this is my decision boundary, and I can just solve this for x2, for example. It does not look like a linear function, but if I just solve it for x2, I would say get x2 is equal to minus a0 over a2 minus a1 over a2 x1. So now hopefully you can see it's a linear function with some, it has some intercept here and some slope, but it's just a linear function, x2 as a function of x1. So this is the decision boundary, which is this red line here, this one here. This is the decision boundary. Everything to the left is classified as fail, and everything to the right is classified as pass. And as before, I see that many points I get right in my classification, but some points I get wrong. So here, for example, this point here would be classified as fail because it's to the left of the decision boundary, but in reality it was a pass. This person passed. And similarly, this point here would be classified as pass because it's to the right of the decision boundary, but in reality it was a fail. So we see how kind of misclassification also applies in this case, and here we see some example how the model, it did perform quite well because it got quite many correct, but some it still got wrong. And we will look in the following at the misclassification rate, and we will also look at some other metrics we can look at, which is called the confusion matrix, which helps us to understand better the error rates of those models. And that's what we will discuss next.